Is it audible, sir?
Yes, sir. Audible, sir.
Okay. So yesterday we have seen properties of that sequence which converges to a real number. And continuing to that lecture, next is tail of the sequence. Tail means, suppose you take a sequence, Sn is a sequence of real numbers. Suppose you take m is a fixed positive integer. Then this Sm plus 1, Sm plus 2, Sm plus 3 after m terms, this is called actually tail of a sequence. In fact, mth tail, we call this as mth tail of the sequence. For example, to take Sn is equals to suppose 1, 2, 3, 4 sequence of natural numbers. Suppose my m is, for example, 100. So what is my mth tail? My mth tail is of Sn is exactly after 100th term, means what? S101, S102, S103, like this. That means S101 is exactly 101, S102 is nothing but 102. This is not 103, like this. So this is about a tail of the sequence, mth tail of the sequence. Suppose take another example. Sm is equals to like 1 by n for n belongs to n, right? Suppose my m is 2. So what is my mth tail of the sequence? Sequence Sn is Sm plus 1 means what? S3. Sm plus 2 means what? S4, S5, S6. That means S3 is nothing but 1 by 3. S3 is nothing but 1 by 3. S4 is nothing but 1 by 4. S5 is nothing but 1 by 5. It's like this going on. So this is about a tail of the sequence. Now, look for what is the relation between tail of the sequence and the properties of the sequence, convergence of the sequence. So let us go to the properties. Suppose first one, Sn suppose converges to suppose S is a real number. So if and only every tail, every mth tail, you can take every m tail of Sn converges to CML. Right? You give me any tail. Suppose Sn, suppose you take this, Sn is equals to 1 by n, such that n belongs to n. Right? So you know clearly Sn converges to 0 as n tends to infinity. We have seen Sn clearly converges to 0. So what is the result says is that every tail that you take, every tail, Sm plus 1, Sm plus 2, Sm plus 3, you take any tail. That means Sm plus 1 is nothing but what? M plus 1. This is m plus 2. This is m plus 3, like this. So this also sequence, this sequence converges to 0 as m tends to infinity. Why? Because this is true for every m. Right? So once the sequence converges to some real number, every tail of the sequence converges to same L. Right? This is the first property. Similarly, second one, a sequence of real numbers that you take, a sequence of real number which diverges to plus infinity as n tends to infinity, if and only every tail, every m tail of Sn diverges to plus infinity. Right? Suppose you take Sn is equals to like n square. So clearly we observe that Sn tends to plus infinity as n tends to infinity. Sn diverges to plus infinity, we have seen. But the thing is, you take any tail, any m tail, You see any m tail, what is this actually? M plus 1 whole square, m plus 2 whole square, like that going on, it tends to infinity as m tends to infinity. Therefore, what you observe is whenever the sequence diverges to plus infinity, of course, every m tail of that sequence diverges to same plus infinity. Third one, similarly, Sn diverges to minus infinity as n tends to infinity. Of course, every m tail of this sequence diverges to plus infinity, plus minus infinity. This is also important idea. Next, what is the rest? Rest is oscillately finitely. Means, suppose Sn is a sequence of real number is oscillating finitely. If or null, if every m tail of Sn is oscillately finitely. You give me any sequence of oscillating finitely sequence. Suppose you take minus 1 whole power n for n equals to 1, 2, 3, 4 going on. So this is my sequence minus 1, 1, minus 1, 1, minus 1, 1, like this going on. We have seen that it is oscillating finitely because the range is finite, neither convergent nor divergent. Of course, its range is bounded. You know, what is my range? My range is bounded, neither convergent nor divergent. Therefore, it is oscillating finitely. Look at its tail, mth tail. This is a definition. Therefore, this is nothing but minus 1 whole power m plus 1, minus 1 whole power m plus 2, going on, going on. Suppose m is even, you're going to get your minus 1. Suppose m is odd, you're going to get your plus 1. So without loss of generality, I'm going to take m is even. So once m is even, m plus 1 is odd. So minus 1, 1, minus 1, 1, minus 1, 1. So it is also oscillating finitely. That this is true for every m because m is not a fixed number, m is arbitrary. This is true for every m. Therefore, every tail that you consider, that is also oscillating finitely. Similarly, you take any sequence, Sn is a sequence, is oscillating infinitely. If or null, if, you know, every m tail of Sn is oscillating infinitely. Right, example, you take this, Sn is equals to minus 1 whole power n into n for n equals to 1, 2, 3, 4 going on. You know, clearly it is oscillating infinitely because it neither convergent nor divergent. This is minus 1, second term is 2, third term is again minus 3, fourth term is 4. Sorry, reverse I am taking now. So first term is minus 1, second term is 2, third term is again minus 1, minus 3, fourth term is 4. So like that. And range is unbounded. So clearly range is unbounded and neither convergent nor divergent. Therefore, it is oscillating infinitely. Right? Clearly oscillating infinitely. And look at any mth tail. M is not fixed. So look at any mth tail. This is the definition of mth tail. So what you get is actually this is minus 1 whole power. By definition, minus 1 whole power m plus 1 into m plus 1. This is minus 1 whole power m plus 2 into m plus 2. Like that going on. So therefore, what you observe, this is also oscillating infinitely. Clearly, it is also oscillating infinitely. So what you observe is that, you know, tail preserves the same structure. Whenever the sequence converges to something, tail also converges. Whenever the sequence diverges to plus infinity, the tail also diverges to plus infinity. Whenever the sequence diverges to minus infinity, the tail also diverges to minus infinity. Whenever the sequence is, you know, oscillating finitely, the tail also oscillating finitely. So this is a behavior of a tail. That means tail preserve the same structure as you consider the sequence. Right? Whatever structure you have, whatever property S has, the tail also the same property. Right? Next is property number 6. So this is a very, very important property which you've seen in basic analysis course. Suppose you take any S is any subset of R. Suppose you take X. X is a limit point of S. X is a real number. X is a limit point of S. If and only if there exists a sequence, of in fact distinct terms sequence in S minus X other than X, right, such that is Xn converges to Sn converges to, you can take this as S, you can take this as S, right? So Sn converges to S as n tends to infinity. So this is clearly happens. Suppose you take a limit point. This is a very standard property. Suppose S is a limit point of S. Automatically one can find a sequence in S minus X such that Sn comes to S. We can easily prove it. Right? Seventh one, not the example actually here is seventh one. Suppose S is a subset of R. Again, S is a limit point of R. S is a point in R. S is in S closure if and only if there exists a sequence. There exists a sequence Sn in this S in such a way that Sn converges to yes. This is also important property, right? Whenever that S is in S closure, if and only if there exists a sequence in S such that Sn comes to yes. So this is also important property. Very, very important property. Next is suppose S is a subset of R and supremum. Suppose supremum of S exists. Suppose you call it as some X. X is a real number. Supremum exists means what? It is a bounded set. Suppose you take like that. So automatically that should be in the closure of the set. That should be in the closure of the set. For example, you start with this. You take this example. S is equals to suppose open 0, 1. So clearly supremum exists because it's a bounded set. Supremum is 1. So and look at the closure of S. Well, closure of S is nothing but what? Here 0 and including 1. Therefore, close 0, 1. So what you observe is 1 belongs to close 0, 1, but 1 is exactly supremum of S. But what is this? S closure. Therefore, supremum of S belongs to the closure of S. So in particular, X belongs to yes if S is closed. So based me chala questions CSR lo vachai. This is very, very important property. If S is closed in R. Means S is closed means what? S closure is equals to S. Yes or no? S closure is equals to S. Right? This is important property. Right? So supremum of X is equals to X. That means X belongs to S closure. X belongs to X closure. S closure. S lo undadandi. For example, ikkada మీరు 1 తీసుకున్నారు. సుప్రీమమ్ ఆఫ్ S ఏంటి 1 వచ్చింది. 1 S లో ఉంటుందా? S లో ఉండదు. అదేనా? S లో ఉండాల్సిన అవసరం లేదు. ఇట్స్ an adherent point. X belongs to S closure. X belongs to S closure. Need not necessarily sitting in the S. Right? Next, similarly, one can extend this idea to infimum. Suppose S is subset of R. Suppose S is bounded below. Suppose infimum is, suppose you take X, which is R. So then automatically X is in S closure. In particular, X is in S if S is closed. This is also important idea, right? Suppose you take this same set that you started with. So what is infimum? Infimum of S is 0. So 0 belongs to S closure. But what is S closure? Close 0, 1. Right? So therefore, this is also very, very important property. Right. Next is 10th one. Algebra of limits. Suppose Sn converges to S and Tn converges to T. So that will always imply that Sn plus Tn converges to S plus T. Understand, this is convergent, belongs to R. So Sn converges to S, Tn comes to T. Obviously, the sum converges to S plus T. So that means sum of the sequence comes to the sum of the limits. Limit of the sum is equals to sum of the limits. But converse, look at the converse. Converse may not be true. Suppose you take Sn is equals to N, Tn is equals to minus N, for N equals to 1, 2, 3, 4 going on. So therefore, Sn plus Tn, what is Sn plus Tn? N minus N plus minus N, that is 0. This is true for every N. Therefore, it's a constant sequence. Therefore, Sn plus Tn converges to 0 as n tends to infinity. Therefore, Sn plus Tn is convergent, but Sn fails to be convergent. Sn is divergent. Right? So converse of the results may not be true. Means if the limit of the sum is equals to sum of the limit, that happens. If the sum is defined that is convergent, that need not imply that individual sequences are convergent sequences. Right? Next, 11th one. Suppose Sn converges to S. S is a real number. Suppose Tn converges to T. T is a real number. Their difference Sn minus Tn also converges to S minus T as n tends to infinity. Right? So, but what about the converse? Suppose you can take Sn is equals to N, Tn is equals to N. Right? What about Sn minus Stn? Sn minus Tn is actually what? N minus N. This is 0 for every N. Right? It's a constant sequence. This is converges to 0 as n tends to infinity with respect to any topology. Therefore, Sn minus Tn converges to 0 as n tends to infinity. So Sn minus Tn convergent, but whereas Sn is divergent. Sn is divergent. Divergent to plus infinity. Right? Similarly, product. Suppose Sn comes to S, S is a real number. Tn comes to T, T is a real number. Then limit of the product is equals to product of the limit. Right? You can verify any standard book. There are a lot of proofs. Go through it. Right? Right? Sn into Tn, which converts to S into T. But what about the converse? Converse, suppose Sn is equals to, you can take Mr. Medan, this coach, you can take 1 by n for n belongs to n. Tn is equals to, suppose you take n for n equals to 1, 2, 3, 4 going on. Right? Therefore, Sn into Tn, what is this? What is Sn? 1 by n into n. Therefore, this is what actually 1. Again, this is a constant sequence. Therefore, Sn into Tn, which converts to 1 as n tends to infinity, but Tn is divergent. But Tn is unfortunately divergent. Right? Next, division, quotient. Suppose Sn comes to S and Tn comes to T, provided T is non-zero, and this Tn is non-zero for every n equals to 1, 2, 3, 4 going on. Then Sn by Tn, which converts to S by T. Again, the converse may not be true. Suppose you take Sn equals to n, Tn equals to same itself. Right? Therefore, Sn by Tn is nothing but what? N by n, that is equals to 1. Again, constant sequence. Therefore, Sn by Tn converges to 1, but Sn fails to be convergent. Therefore, converse may not be true. So this is also very important property when you take the algebra. Right? Next is, suppose you take this. 14th. Suppose Sn diverges to plus infinity, and suppose you can take Tn diverges to plus infinity. You can write all else. Obviously, Sn plus Tn diverges to plus infinity. Right? Sum of divergent sequences means plus infinity. Always diverges to plus infinities. Sn diverges to plus infinity, but Tn also diverges to plus infinity. That will imply that Sn plus Tn diverges to plus infinity. You can go through any standardized book, you can have a proof. But converse, again, need not be true. Suppose you take Sn is equals to 2n, right? Or else you can take Sn is equals to, what you take, suppose you can take anything. Sn is equals to n, Tn is equals to 2n. You can take. I need to have, what is this? I need to have Sn plus Tn converges, right? I'm going to take Sn equals to 1, Tn equals to 1. Right? So therefore, what you observe is Sn plus Tn is equals to n plus 1 for n equals to 1 to 3, 4 going on. Therefore, clearly it is unbounded. Of course, it diverges to plus infinity. Right? This is 2. When you substitute n equals to 1, 2, when you substitute n equals to 2, 3, 4, like this, it towards plus infinity. By Archimedean property, one can show that this tends to plus infinity. So Sn plus Tn diverges to plus infinity as n tends to infinity. But Tn is convergent. Tn is convergence to plus 1 as n tends to infinity. So converse may not be true. Right? Similarly, 15th, whenever Sn diverges to minus infinity, Tn diverges to minus infinity, obviously Sn plus Tn also diverges to minus infinity as n tends to infinity. Right? This is also same idea. Right? But the converse may not be true. Suppose you, for instance, you can take n equals to minus 1 and Tn is equals to minus 1 for n equals to 1, 2, 3, 4 going on. So what you observe is Sn plus Tn is equals to minus n minus 1 for n equals to 1, 2, 3, 4 going on. Therefore, this towards minus infinity. When you substitute n equals to 1, this is minus 2, this is minus 3, like that going on. Therefore, Sn plus Tn, one can easily check it by Archimedean property. You can go through the proof. So this is Sn plus Tn diverges to minus infinity as n tends to infinity. Right? But what happens? This Tn fails to be divergent. So Tn is convergent. In fact, it converges to minus 1 as n tends to infinity. Right? Next is 16th. Sn converges to plus infinity. Tn converges to minus infinity. The problem comes. So we can have so many feasibilities. First one, right? Sn plus Tn may converge. You can take like this. This is my Sn plus Tn. So Sn plus Tn may converge. Example, suppose you take Sn is equals to n, Tn is equals to like minus n. So clearly we observe that Sn tends to plus infinity, Tn tends to minus infinity. So clearly the hypothesis is satisfied. Clearly hypothesis is satisfied. Just you need to justify, you need to verify that whether Sn plus Tn converges or not. So Sn plus Tn clearly, this is n minus n, this is 0. Therefore, Sn plus Tn is a constant sequence which converges to 0. So what you have seen is Sn divergent to plus infinity, Tn also diverges to minus infinity, that will imply that Sn plus Tn is convergent sequence, may be convergent. So we have seen example. Of course, it diverges to plus infinity. Example, suppose you take this. Suppose Sn is equals to minus n. This Sn is equals to 2n and Tn is equals to minus n. So clearly we observe that 2n is towards plus infinity, therefore it tends to plus infinity, and Tn diverges to minus infinity. So clearly hypothesis is satisfied. But look at the sum of these two sequences. Sn plus Tn is nothing but 2n plus minus n. This is exactly 2n minus n. That is exactly n. You know, it is tends to plus infinity as n tends to infinity by Archimedean property. Right. Therefore, what you observe is, so the sum may diverges to plus infinity also. So that means again the sum diverges to minus infinity also, maybe. Suppose you take Sn is equals to n, Tn is equals to minus 2n. So what you observe is, you know, Sn diverges to plus infinity clearly, and Tn diverges to minus infinity, no doubt. Right? But the thing is, whenever Sn plus Tn, look at the sum, but the sum, what is this? This is Sn minus 2n is exactly what? Minus n. You know, this tends to minus infinity as n tends to infinity. Therefore, Sn plus Tn may diverge to minus infinity. Right? Again, there is another feasibility. It may oscillating finitely. Right? So can you give the counter? Suppose you take Sn is equals to minus 1, minus 2, minus 3, minus 4, like this. Tn is equals to, suppose you take this 1, 3, 0, I'm going to get 1, 3, 5, 5. This is what? Minus 5, 6, minus 6. You can write properly. This is minus 5, minus 6, minus 7, dot, dot, dot. So what is this? What is the seed? This is exactly minus 7, 7, 7, comma 7, dot, dot, dot going on. That means once you take the sum, what you get? 0, 1. The sum is 0, again 0. The sum is again 1. The sum is 0 again, 1, 0, 1, 0, 1, 0, like this. So therefore, clearly Sn plus Tn is oscillating finitely, but Sn diverges to minus infinity, of course, is diverges to plus infinity. Therefore, what you observe is, you know, so may oscillating in. సో మీరు ఇంటర్చేంజ్ చేయండి, మనకు కావాల్సింది ఏంటి? ప్లస్ ఇన్ఫినిటీ కావాలి కదా, దీన్ని Tn తీసుకోండి బెస్ట్. దిస్ ఇస్ Sn. So therefore, this is oscillating finitely. So similarly, one can think of example which is oscillating infinitely. Right? So ఎప్పుడు problem problem we can have a problem that we are facing is whenever Sn tends to plus infinity, whenever Tn tends to minus infinity, we are really facing a problem. We don't know whether it is convergent, the sum is convergent, whether the sum is divergent to plus infinity, the sum is divergent to minus infinity, whether it is oscillating finitely. We don't know about the sum. So there is a problem actually. So Sn diverges to plus infinity, Tn diverges to minus infinity. We don't guess. Therefore, what you think is no conclusion. So what is your answer? What is your answer? General answer, that is whenever Sn diverges to plus infinity, at least one of them is diverges to minus infinity, Sn plus Tn has no conclusion. I don't know whether it is convergent or divergent or oscillating finitely. I don't know anything. right? And this is property number 16. Next to property number 17. Suppose Sn is divergence to plus infinity, and infimum of Tn, infimum of the sequence, this infimum of the sequence is bigger than minus infinity. So obviously Sn plus Tn diverges to plus infinity. Suppose, can you give an example? We can take an example. Sn is equals to like n, and Tn is what? Actually, I'm going to take, suppose, bigger than minus infinity. So that means, suppose you take, you can take infinity, in fact, right? So Sn clearly diverges to plus infinity, and infimum. What is the infimum of this? What is the infimum of this? Tn. Tn is 1, 2, 3, 4 going on. This is my Tn. What is infimum? That infimum of Tn is actually what? Is plus 1. So 1 is always bigger than minus infinity, right? So by this result, I'll give you later examples. This is only theory, right? So this tends to plus infinity, right? This is also very important result, very, very important result. I'll show you why this is important. I'll show you later. These are the only property class. So next is Sn, suppose diverges to plus infinity, and suppose take the limit of Tn exists. Already told you what is meant by limit of exists. Limit exists means whether it is if it is convergent or divergent. If it is convergent or divergent, we can say that limit exists. So limit exists. Limit is bigger than minus infinity. That will imply that Sn plus Tn diverges to plus infinity. This is also very important result. We'll see what is the importance of this. Right? So limit exists, which is bigger than minus infinity. All right. Suppose I'll give an example. I'll give later example. So this is also important example, important property. Sn diverges to plus infinity. Limit also bigger than minus infinity. You can think of this Sn is equals to n simply. Tn is equals to like you can take anything. In fact, so suppose you take in fact n square. So Sn diverges to plus infinity clearly, and Tn also diverges to plus infinity. This limit of Tn is actually what? Plus infinity, which is bigger than minus infinity. Therefore, by the results tells you that Sn plus Tn diverges to plus infinity. Right? This is also very, very important famous result. Right? Next is Sn diverges to plus infinity, and whenever Tn is bounded, obviously Sn plus Tn diverges to plus infinity. Sn plus Tn diverges to this. Suppose we take Sn is equals to this, like Tn is equals to minus 1 whole over n. Suppose you take this. So obviously what you have is, Sn diverges to plus infinity clearly, and Tn is a bounded sequence. So by the result says that, Sn plus Tn diverges to plus infinity. By the results tells you that Sn plus Tn diverges to plus infinity. So converse may not be true in general. So look at the converse in general may not be true. We can give a lot of examples. Suppose you can take Sn is equals to n, Tn is equals to n, right? So what is Sn plus Tn? 2n. So 2n diverges to plus infinity as n tends to infinity. But what about Tn? Is it bounded? So Tn is unbounded. We can give a lot of examples. Right? The thing is, this is also very, very important theorem, a very important problem, very, very important problem, because we'll have an exercise problems. Later I'll tell you. This is only theory session. Before yesterday we also, right? We have seen the theory session. Right? This is property number this. Similarly, we can analog to this. Similarly, we can suppose property number 20. Right, so we can take this product Sn, suppose diverges to plus infinity, and suppose Tn diverges to plus infinity. Sn into Tn diverges to plus infinity. Right, so this is quite possible by the definition, but the converse may not be true. You take Sn is equals to n square. Suppose Sn is equals to n and Tn is equals to 1. Therefore, what happens? Sn into Tn is actually what? N into 1, that is n. This is true for every n. This diverges to plus infinity as n tends to infinity. But Tn is convergent. So converse may not be true.
In property, Tn tends to infinity, sir.
Converse, we were looking for converse. Okay, converse may not be true.
Okay, sir.
Right, we are looking for the converse. Okay. 21. Suppose Sn diverges to plus infinity and Tn diverges to minus infinity. Obviously, the product diverges to minus infinity. Right? What about the converse? Is the converse true? Suppose Sn is equals to 1, Sn is equals to n, looking for suppose minus n, Tn is equals to minus 1. So Sn into Tn minus n into minus 1, that means n. This tends to plus infinity as n tends to infinity, but Tn is convergent. Of course, Sn also diverges to minus infinity, not plus infinity. So converse may not be true. Right? 22. And we've seen Sn diverges to
Tn diverges to plus infinity. Yes. Sn into Tn diverges to minus infinity.
We'll take this plus 1. Is it okay? Is it okay?
Okay. Sir.
Minus infinity. All right. Next to property. Sn diverges to. You've seen whatever seen actually. Yeah. Suppose Sn convergent. Sn is diverges to minus infinity. Tn diverges to minus infinity. Their product also diverges to plus infinity. It's also straightforward. Right? So whatever the converse, you can take Sn is equals to suppose n, Tn is equals to 1. That's enough. Right? For n equals to 1, 2, 3, 4 going on. So therefore, Sn into Tn is equals to n, diverges to plus infinity, but Tn fails to be, diverges to plus minus infinity. Therefore, converse may not be true. Right? Next is
Sn is minus n.
Sn diverges to plus infinity, and limit exists.
Statement
Limit
minus
is positive.
plus.
Yeah. Exists. That will imply that Sn into Tn diverges to plus infinity. Right? But the converse may not be true. Suppose you take this Sn is equals to n, Tn is equals to, suppose you can take 1 by n, not 1 by n, you can take 1 by n, you can enlarge this n square. Right? Therefore, Sn into Tn is what actually? N square into 1 by n. If this is exactly n, this tends to infinity plus as n tends to infinity. But the thing is Tn convergent. In fact, Tn converges to 0. Right? Tn converges to 0. But what is actually theorem tells you the limit must be positive. But what you are getting here, limit is 0. Limit of Tn is 0. It's never be positive. Right? Converse may not be true. Right? So 24. Whenever Sn diverges to plus infinity, limit of Tn is negative. Sn Tn diverges to minus infinity. This is also straightforward. You go through it. So what about the converse? Again, the converse may not be true. So suppose you take Sn is equals to like n. You can take Sn is equals to n square minus n square. Tn is equals to like 1 by n. Right? So therefore Sn into Tn, what you get? Minus n. This diverges to minus infinity as n tends to infinity. But Tn again converges. The problem comes. Right? So this is also important thing. Right? Next is ఇది ఎప్పుడైనా లిమిట్ 0 అయింది అనుకోండి, అప్పుడు యాక్చువల్గా గెస్ చేయడం కష్టం. ఈ లిమిట్ ఎప్పుడైనా పాజిటివ్ అన్న కావాలి, నెగిటివ్ అన్న కావాలి. ఈ 0 అయినప్పుడు నో కంక్లూషన్. వాట్ అబౌట్ దిస్ లిమిట్ ఆఫ్ Tn 0 అయితే ఏమవుతుంది? యూ నీడ్ టు నో ఇట్ యాక్చువల్లీ. డోంట్ హ్యావ్ ఎ కంక్లూషన్. ఇన్ ఫ్యాక్ట్ వీ డోంట్ హ్యావ్ ఎ కంక్లూషన్. రైట్? సపోజ్ నేను Sn ఈజ్ ఈక్వల్స్ టు n ఇస్తాను, Tn ఈజ్ ఈక్వల్స్ టు 1 by n ఇస్తాను. రైట్? Tn equals to 1 by n ఇస్తాను. What is Sn into Tn? Go through it. Sn is equals to n ఇస్తాను. Tn equals to 1 by n ఇస్తాను. What is Sn into Tn? Exactly 1. This tends to 1 as n tends to infinity. Okay. So ఇక్కడ Tn converges to 0 అయింది. Sn diverges to plus infinity అయింది. బట్ ఇక్కడ diverges to plus infinity అయిందా? కాలేదు. రైట్? సపోజ్ Sn is equals to నేను ఏమి ఇస్తాను? n స్క్వేర్ ఇస్తాను, మైనస్ n ఇస్తాను, లేకపోతే n స్క్వేర్ n మీ ఇష్టం. Tn is equals to what? ప్లస్ ఇన్ఫినిటీ అయినా మైనస్ ఇన్ఫినిటీ రావాలి కదా. రైట్? ప్లస్ ఇన్ఫినిటీ అయినా రావాలి, మైనస్ ఇన్ఫినిటీ. సపోజ్ యూ టేక్ డైవర్జెంట్ వచ్చేది ఒకటి చెప్పండి. డైవర్జెంట్ సపోజ్ Sn is equals to ఎట్లా తీసుకుందాం, -1 whole power n by n. Therefore Sn into Tn ఏంటి యాక్చువల్లీ? -1 whole power n. సో ఇది నైబర్ డైవర్జెంట్ కాదు, కన్వర్జెంట్ కాదు. బట్ థింగ్ ఏంటి? ఇది డైవర్జెస్ టు ప్లస్ ఇన్ఫినిటీ, కన్వర్జెస్ టు 0. ఇది ఆసిలేటింగ్ ఫైనైట్లీ. సో నో కంక్లూషన్ అన్నమాట. 0 అయినప్పుడు ఇది వన్ ఆఫ్ ద లిమిట్ 0 అయినప్పుడు ఈ లిమిట్ ప్లస్ ఇన్ఫినిటీ అయ్యి ఇది 0 అయినప్పుడు కంక్లూషన్ ఇవ్వలేము. సో ఇది జాగ్రత్తగా గమనించాలి. ఓకే, అందుకే నేను రాసింది లిమిట్ షుడ్ బి పాజిటివ్, నెగిటివ్కి రాశాను. రైట్? లిమిట్ షుడ్ బి పాజిటివ్ అండ్ నెగిటివ్కి రాశాను. జాగ్రత్తగా చూడండి. ఓకే,
ఎగ్జామినేషన్ పాయింట్ ఆఫ్ వ్యూ ఇలా అడగడానికి స్కోప్ ఉంది కదా సార్?
యా సార్, ఇవే అడుగుతాడు, ఎక్కువ స్ట్రెస్ చేసి అడుగుతాడు. లిమిట్ 0 ఎందుకు తీసుకోరు? 0 తీసుకుంటే అయితే.
ఇంపార్టెంట్ ప్రాపర్టీ.
నెక్స్ట్ ఈస్ ప్రాపర్టీ నెంబర్ 25. Suppose Sn is a sequence of, this is very standard property in complex analysis, of course in real analysis also, a sequence of real numbers. In fact, sequence of positive real numbers. In order to show that Sn diverges to plus infinity, it's enough to show that limit of the reciprocal of this tends to plus infinity, 0. In order to show that something tends to plus infinity, you need to show that limit of the reciprocal should be 0. Suppose example, you can take Sn is equals to like n square plus n amma, n square plus n. You are asking for the limit. I want to show that this tends to plus infinity. You know, it is a sequence of positive real numbers. Clearly the sequence of positive real numbers, no doubt. Sn is positive for all n. And you are looking for the limit, whether it diverges to plus infinity or not. So look at the limit of the reciprocal. But the thing is, the limit of the reciprocal is 1 by n square plus n. But the limit of the reciprocal, n is large. Whenever n is large, again background property, this is 0. So limit of the reciprocal 0 means the sequence tends to plus infinity. So this is also very standard property in complex analysis as well as real analysis. 26. Sn diverges to plus infinity. My k is positive real number. Obviously, Sn and k into Sn diverges to plus infinity. K into Sn always diverges to plus infinity. Right? This is also straightforward, but the converse may not be true. Suppose you can take Sn is equals to minus n. Suppose you can take k equals to minus 1. Right? K into Sn is not minus 1 into minus n. It's exactly n. This diverges to plus infinity as n tends to infinity. But the thing is here k negative. Right? But the thing is k is negative. So converse may not be true. Similarly, Sn diverges to plus infinity. Whenever k is negative, k into Sn diverges to minus infinity. Right? Again, the converse may not be true. Suppose you can take Sn is equals to n, k equals to, suppose you take Sn is equals to minus n, you can take k equals to 1, you can take. All right. So therefore, Sn into kn, k into Sn is equals to exactly minus n into 1, that is exactly minus n. This tends to minus infinity as n tends to infinity, but k here is positive. So converse may not be true. See, what about k equals to 0? Again, no conclusion. Understand? No conclusion. In k equals to 0 గురించి మాట్లాడదలుచుకోలేదు. You need to go through the counter examples, right? So k 0 కి చెప్పలేమన్నమాట. Okay, same examples ఇచ్చుకోండి. Okay, next, yeah, we'll see problems. Suppose Sn is equals to, you can take example minus 1 whole power n into 1 plus 1 by n. Question is it divergent or convergent? So which of the following is true?
1 minute time ఏంటి సార్ చూద్దాం.
Yes, sir. First one, Sn is convergent.
Please respond in chat box. Please give your answer.
Sn is divergent to plus infinity. The third one, Sn is divergent to minus infinity. Fourth one, Sn is oscillating sequence. Yeah, most of them responded oscillating.
Rishma responded.
Akshaya, Mamta. సో ఇట్లాంటి క్వశ్చన్స్ వచ్చినప్పుడు కొంచెం కేర్ఫుల్గా ఉండాలి. ఎందుకంటే ఈ -1 హోల్ పవర్ n వచ్చినప్పుడు క్వశ్చన్స్ ఎంట్రన్స్లో వస్తున్నాయి, డిఎల్లో కూడా వచ్చినాయి, నేను చూశాను. సో ఈ -1 హోల్ పవర్ n వచ్చినప్పుడు ఎట్లా చేయాలో కూడా చెప్పాను మీకు. యాక్చువల్గా there are so many ways, but the thing is, simple way is split the set into 2 pieces. Right? When you take n is even, what you get? -1 whole power n is like this. Whenever n is not, -1 whole power n is exactly this. Then the problem becomes easy. Now we can think of what is the sequence, whether it is convergent or divergent or oscillating finitely. So whenever n is equals to 1, what happens? Whenever n is equals to 1, is exactly what? 1 plus 1, 2 minus 2. Minus 2 is exactly here. Whenever n is equals to 2, what you get? N equals to 2 means 2 plus 1 by 2. That means 3 by 2. Whenever n equals to 3, n equals to 3 means what? Again, 1 plus 1 by 3. That means 4 by 3 minus 4 by 3. Minus 4 by 3 ఇక్కడ ఉంటుందా లేదు ఇక్కడ ఉంటుందా? రైట్. సో 2 less than 4 by 3 కాదు కదా? So therefore 2 bigger than 4 by 3. Yes or no? Therefore minus 2 is always less than minus 4 by 3. Minus 2 is always less than minus 4 by 3. Therefore this is wrong answer. 2 bigger than 4 by 3. Is it okay? So minus 2 is always less than minus 4 by 3. Therefore this is always true. Next, n equals to 4. What is n equals to 4? See, ఒకటి అక్కడ ఒకటి ఇక్కడ వచ్చిందంటే ఆసిలేటింగ్ అనేది మనకి ఈజీగా అర్థమైపోతుంది. నెక్స్ట్ ఏంటి? n equals to 4. 4 అంటే ఏంటి? ఇక్కడ ఈ సెట్లో ఉంటుంది. 1 plus 1 by 4. 1 plus 1 by 4 అంటే 5 by 4. రైట్. 5 by 4 ఎక్కువ ఉంటుందా? చూడండి తక్కువ ఉంటుందా? 10, 12. ఓకే, ఇన్ఈక్వాలిటీ సాటిస్ఫై అవుతుంది. సో దిస్ ఇస్ స్ట్రిక్ట్లీ లెస్ దెన్. ఓకే, నెక్స్ట్ n equals to 5. 5 అంటే ఏంటి? అగైన్ minus 5 by 4 ఇక్కడ ఉంటుంది. నెక్స్ట్ n equals to 6. 6 అంటే 7 by 6 ఇక్కడ ఉంటుంది. మీన్స్ 28, 30. ఓకే, నెక్స్ట్ ఇక్కడ అగైన్ 6 తర్వాత ఏంటమ్మా ఇక్కడ రాంగ్ రాస్తాను. ఇక్కడ ఏంటి మైనస్ దగ్గర ఏం చేస్తాను? 6 దగ్గర ఏం చేస్తాను? 7 by 6 ఇక్కడ. ఓకే, 5 దగ్గర ఏం చేస్తాను? 5 దగ్గర 5 plus 1 6 వస్తుంది కదా ఇక్కడ. సో 5 దగ్గర ఏమొస్తుందమ్మా? 5 అంటే 6 by 5. సో వాట్ యూ అబ్జర్వ్ ఇస్ దిస్ టెన్స్ టు -1, అగైన్ దిస్ టెన్స్ టు +1. సో ఇప్పుడు చెప్పండి, ఇది ఆసిలేటింగ్ ఫైనైట్లీయా, ఆసిలేటింగ్ ఇన్ఫైనైట్లీయా? ఇట్స్ ఎ బౌండెడ్ సీక్వెన్స్, నో డౌట్. రైట్, ఫర్ ఎవ్రీ n. therefore it's a bounded sequence. వన్ టర్మ్ ఇట్లుంటే వన్ టర్మ్ ఇటు ఉంది, వన్ టర్మ్ ఇటు ఉంటే వన్ టర్మ్ ఇటు ఉంది. సో వాట్ ఈస్ ద సీక్వెన్స్? ఇది కన్వర్జెంట్ అయితే కాదు. ఎందుకు? దిస్ సీక్వెన్స్ కమ్స్ టు +1, therefore 1 is a limit point of a sequence. This sequence comes to -1, therefore this is also limit point of a sequence. Limit point of a sequence. సో మీకు చెప్పాను, సీక్వెన్స్ కన్వర్జెంట్ అయితే యూనిక్ లిమిట్ పాయింట్ ఉంటుందని చెప్పాను. సో దీనికి యూనిక్ లిమిట్ పాయింట్ లేదు కాబట్టి కన్వర్జెంట్ అయితే 100% కాదు. కన్వర్జెంట్ అయితే 100% కాదు. డైవర్జెస్ టు ప్లస్ ఇన్ఫినిటీ అయితే అంటే కాదు, బికాస్ ఇట్స్ బౌండెడ్. రైట్, ఇది కూడా కాదు, ఇది కూడా కాదు. therefore what is answer? Oscillating sequence. In fact, oscillating finite sequence.
సార్ దీన్ని సమ్ ఆఫ్ 2 సీక్వెన్సెస్ గా రాసుకోవచ్చు కదా సార్? -1 power n into 1 plus -1 power n into 1 by n.
-1 whole power n into
1 plus -1 power n into 1 by n.
అట్లా కూడా రాయొచ్చు, ప్రాబ్లం ఏం లేదు.
Oscillating finitely, then this is divergent.
ఇట్లా కూడా రాయొచ్చు.
One is finite, oscillating finitely, another one is divergent. Sum of these two is oscillating finitely.
ఇది కన్వర్జెంట్.
Yes, sorry, this is convergent.
ఇది కన్వర్జెంట్ 0.
Yeah.
ఇది ఆసిలేటింగ్ ఫైనైట్లీ.
Therefore total sequence is oscillating finitely.
సమ్
చెప్తారా అట్లా?
సో ఐ డోంట్ థింక్ సో. సపోజ్ యు టేక్
Okay sir, okay, no problem.
you can take -1 whole power n. You can take 0.
Is there any
So-
properties are like that?
ఒకటి ఆసిలేట్ థింగ్ ఏంటంటే
Oscillating one is convergent. Oscillating is convergent.
క్లియర్లీ అంటే థింగ్ ఏంటంటే సార్, ఇదైతే కన్వర్జెంట్. సపోజ్ ఇది కన్వర్జెంట్ అయింది అనుకోండి,
Hmm.
సపోజ్ ఇట్ కన్వర్జెంట్ అనుకుంటే ఏమైంది సార్? వాట్ హ్యాపెన్స్ ఈస్, లెట్ us go to this question carefully. Suppose it is convergent. Suppose this is convergent. I don't know whether it is convergent or divergent. Suppose it is convergent. So therefore, this is also convergent. We know. Okay. So difference of convergent sequence is convergent. We have seen. That means -1 whole power n is convergent. Is it convergent? So conduction. Okay. So this is the best technique, right? So this is, suppose you assume that it is convergent. This is convergent. This is convergent. Therefore, difference is convergent. But what is the difference? -1 whole power n is convergent. But is it convergent? Wrong. Conduction. Why are you getting conduction?
So-
Once you assume that this is convergent.
Okay, sir. Right.
Okay. కానీ కన్వర్జెంట్ కాదని చెప్తాం కానీ ఇది ఆసిలేటింగ్ ఫైనైట్ అని మాత్రం we don't have an
Okay. Okay. Thank you, sir. Thank you. Thank you very much.
right. Suppose you take this question number 2. Sn is equals to 3 where n is odd. This is 1 by n where n is even. Yeah. Whether it is convergent, which of the following is right? First one, Sn is bounded. Second one is Sn is convergent. Third one is Sn is oscillating. Fourth one is Sn subsequent ability. Okay. Infimum of Sn diverges to, in fact, divergence. Yeah, use chat box. Naresh Kumar Chandra, 1 2 are correct. Bounded oscillating, option AC. Yes, it was bounded. Okay, and so look at the question. First, plot the real line. Plot the points on real line. This is n is equals to 1 means 3. N equals to 2 means 1 by 2. I need to write like right side. So this is my 3. N equals to 2 means 1 by 2. N equals to 3 means again R3 means again here. S1 here, S3 here, S2 here. This is my S2. Next, S4, 1 by 4, decreasing. Next, S5 is again 3. S6 again here, 1 by 6. S7 is again here. That means it towards 0. Right? It towards 0. But the thing is it convergent or that is my question. So clearly it is bounded, no doubt. Because what is this? So it is bounded below by 0, bounded above by 3. Because all the values lying between this and this. Yes or no? Lying between this and this. Therefore, clearly bounded. There is no doubt. Question is it convergent or not? So
Not
look at that.
convergent.
look at this. Actually, how many terms here? There are so many infinitely many terms. So clearly 3 is a repeating infinitely many. I tell you one property. Whenever the term is repeating infinitely many times, that is a limit point of the sequence. So the terms which are S1, S3, S4 converges to class 3. Therefore, which is repeating infinitely many is a limit point of a sequence. 3 is a limit point of a sequence. Again here, this sequence of even terms towards 0. Sequence of even terms towards 0 as n tends to infinity. Therefore, 0 is a limit point of a sequence. Right? We have seen. So we can have two distinct limit points. Therefore, Sn is not convergent. We have seen whenever it is convergent, it has a unique limit point. Right? Yeah. Is it oscillating sequence? Yes, because one term is here, one term is here, one term is here, one term is here. So it is oscillating. So therefore, it is oscillating, in fact, finitely because bounded sequence. Is it divergent? No. So answer A and C. Answer A and C. తొందరపడకుండా చేయండి. ప్రాబ్లం చేస్తే పేషెన్స్ తో చేస్తే మీకు మంచిగా ఉంటుంది. రైట్? సపోజ్ Sn is equals to 1 plus 1 by 2, 2 plus 1 by 2, 1 plus 1 by 3, 2 plus 1 by 3, 3 plus 1 by 3, right? 1 plus 1 by 4, 2 plus 1 by 4, 3 plus 1 by 4, 4 plus 1 by 4. Question is, which of the following is true? Right? First one, Sn is convergent. Right? Second one is B. Sn has a limit point. C. Sn is divergent. D is oh my struck again.
Yeah, think about the answer, all of you. 1 plus 1 by 2, 2 plus 1 by 2.
Yeah. Is it visible, sir?
Yes, sir. Now okay, sir.
C is Sn is divergent. D is none.
Naresh Kumar B. Yeah, good.
Chandra has 3.
3 divergent. Respond others also. M. Satish. Anusha C. Okay, BC, Naresh Kumar BC. What are the limit points?
So limit points, and guess the limit points. Okay. So it treated as an exercise. Do it. Okay.
Yes, sir. Correct, sir.
Treated as an exercise.
The problem is, sir, they can think.
Okay. So for problem number 2, Sn is equals to 1 plus 1 by 2, 1 by 2 square, 1 by 2 power n. So the following is true. A. Sn convergent. B. Sn is monotonically increasing. C. Sn has supremum of Sn belongs to, you need to take like this, is as Sn as a take like this. So can you say this is supremum? Denote like this. Supremum of the set belongs to the sequence, and infimum of the set belongs to the sequence. The supremum of Sn belongs to this Sn, and the infimum of the set does not belongs to Sn. And E supremum of Sn belongs to Sn, and infimum of Sn belongs to Sn. And F supremum of Sn does not belongs to Sn, infimum of Sn does not belongs to Sn. Right. So this is an interesting question. Do it. So limit of this sine of n pi by 3 divided by root n is equals to answer A 1, answer B 2, answer 3, C 0, answer D 4. Next, limit of sine of n pi by 3, or else you can take simplest example by 2. Answer A does not exist. Answer B 0, answer C 1, answer D minus 1. Okay, do this.
Yeah,
And
start box also. Yes, sir. Good questions. Nice. WhatsApp లో దీనికి solutions discuss చేయండి. Yeah, Naresh Kumar is saying answer is 1. Yeah, correct. You are correct.
and again exercise limit of
Sir, once show previous question, sir.
yes,
మేడం మీ
yes.
నోట్స్ వస్తుంది మేడం. నోట్స్ మీకు వస్తుంది కదా మేడం, యాజ్ టీజ్ గా చూడండి. sin n pi by 3 by root n.
root n
Sin n pi by 3 by root n.
root n and limit n tends to infinity. Answer A 3, answer B 0, answer C minus 1, answer D 1. Is also important exercise. Next is Sn is equals to 0, 1, 1 by 2, 2 by 2, 1 by 3, 2 by 3, 3 by 3, 1 by 4, 2 by 4, 3 by 4, 4 by 4. So the set of all limit points Sn, first one, this is exactly Q intersection with close 0, 1. Yes, R minus Q intersection with close 0, 1. Answer 3 is open 0, 1. Answer 4 close 0, 1. Is also important exercise. Okay, with this I conclude. Do you have any doubt?
Okay, sir. Thank you, sir. Thank you very much.
Okay, sir. Right.
ఓకే, ఈ ప్రాబ్లమ్స్ అన్ని గ్రూప్ లో డిస్కస్ చేయండి. దెన్ సండే రోజు కంప్లీట్ గా రియల్ అనాలిసిస్. టుడే నైట్ ఆర్ టుమారో మార్నింగ్ ఐ విల్ సెండ్ యువర్ మార్క్స్ ఇన్ టెస్ట్ సిరీస్ 3. ఇంకా హైయెస్ట్ ఎవరికి వచ్చినాయి కూడా మీరు గ్రూప్ లో సెండ్ చేస్తానండి. మెరిట్ టాప్ 5 ఎవరున్నారు, టాప్ 5 హైయెస్ట్ మార్క్స్ ఎవరున్నారు కూడా మీరు గ్రూప్ లో పెట్టేస్తాను. వీలైతే నైటే పెట్టేస్తాను. ఇంకెవరైనా ఎగ్జామ్ రాయని వాళ్ళు ఉంటే